Hi, welcome back after the break to all the talks online. Next up is Casey Rosenthal, who's going to speak about continuous verification and the myths of reliability. I'm very interested to hear your talk, Casey, because I've heard about continuous delivery, continuous integration, but never about continuous verification. I do have heard about the myths of reliability, but I'm really interested to see your points on that. So please take the floor.
Cool. Thanks a lot. Can you hear me all right?
Yeah, you're set up.
Great.
You can just share your screen.
Yep. Okay. You should be able to see the words continuous verification and the myths of reliability now.
Yeah.
Great. Cool. And hopefully we have a good Q&A session at the end here. I hope to not just introduce the topic of continuous verification, but say some things that are hopefully controversial to some audiences. So my name's Casey Rosenthal. Let me make sure the slides advance here. I work for a company called Verica, but I'm not really going to talk about that. So I'm just going to dive into it. In the 1480s, I was a port carpenter and occasional boswing in the port of Palos. I worked for a gentleman named Juan de la Cosa, southern coast of Spain. And I got to work on this ship. Well, I couldn't find a photo of it, but here's a painting of this ship, now called the La Galega. And one day in the late 1480s, a VC-backed startup came into town. And back then, VC was a little bit different. The way it worked, this particular startup, because of his backers, had a different legal structure behind him. So he was allowed to impress 3 ships into his service for this new startup venture that he was undertaking. And like most startups, he wanted to be data-driven about which ships he took. So they ran a study, and they looked at a couple different factors for all of the ships in the ports and all along the southern coast and even into parts of Portugal. And so they looked at 3 things for these ships. Well, a lot of things, but 3 things in particular: how successful the ships were with their captains, how risky the captains were, and what the mortality rate was on their ships. But essentially, looking at how safe the ships were. And just to paint a little bit of background at the time, there was a lot of wealth to be made, a lot of success to be had at the time, fishing, cod in particular, off of the northwestern Atlantic, off the coast of what's now the United States. But it was very risky, particularly even just going around Portugal was a very risky place to go fishing. And of course, the maps back then that identified where the cod was, those were all proprietary. They hadn't yet really figured out the benefits of open source at that time. So there was a lot of data to go through, and found some interesting results. First of all, the big success comes with big risks. So it wasn't surprising that the captains who were a little bit riskier had better success. And now everybody was starting off essentially from a level playing field. The typical life of a captain is you'd wake up in the morning, check a smartphone, look at the weather report, and everybody was getting the same weather report, right? So some of those captains, saw a foggy weather report and thought, oh, we'll be fine. And others thought, oh, okay, that looks like inclement weather. We'll stay home, sit this one out. So it makes sense that the ones that took more risk were more successful. What was surprising is that the ones who took more risk also had lower mortality rates. The ones who took more risk were safer. They had better safety records. And this was really fascinating to me. So this kind of kicked off my interest in resilience engineering and reliable systems. And And so how do we explain that result? Well, the captains and the crews that experienced inclement weather, that experienced bad fishing conditions, basically built up over time levels of experience and ways of coping and adapting to unpredictable circumstances, so that when a really bad storm came in, which was usually a surprise, they had the skills to know how to navigate it and successfully deal with that situation. Whereas the ones who avoided that experience, basically when they got caught by surprise, there was nothing that they could do about it. They didn't have the skills to handle that kind of situation. If you look closely, I don't know how this carries over screencasting. You can see me in the painting there. That's where I am. So a few years later, many years later, I got into shoe cobbling, which was a really great business. This was my mentor for a while. So this is in the 1850s. I was in Chillicothe, which was a big metropolis in Ohio at the time. Shoes were a really great business to be in the 1850s, because cities back then were filthy. It wasn't like a modern city like San Francisco. If you walk down the street today, it's super clean. Back then, the streets were just, frankly, disgusting. So if you were in the shoe business, people had to go through shoes really often. So being in the shoe business, you had a steady clientele. And so I worked for this shoe manufacturing retail store, and it got so popular that they would hit these peaks where they would have like thousands of orders per second. It's really good business, really filthy cities, so people had to change their shoes really often. And in order to handle that kind of load, we had to change the retail experience. So basically, people would come up and place orders, and then we would have people, we call them racers, who would race back to a blackboard and put chalk marks next to the kind of shoe that was being requested, that was being bought. And we would have other racers who would run back to the warehouse to get it and come back and hand it off, so that it could be run up to the front of the store. And when we had this much traffic, sometimes things would get a little out of hand. In fact, they called the blackboard the zoo. And there was a keeper of the zoo, and things would get kind of hectic there. And sometimes they would get so hectic that people would get impatient and put another line of chalk next to the product, because they would assume the first one wasn't seen. And then, when they got the shoes, they would go up, and some people would be standing there left with an extra pair of shoes. So things got out of hand, and eventually that blackboard got so bad, so out of alignment with reality, that the shoe store, that the whole operation had to be shut down, so that they could retake inventory, of the stock of shoes that they had, basically clear that chalkboard off and start over. Took over 24 hours. And the problem was, without having access to shoes, nobody wanted to go outside. So basically, all of the businesses on Main Street shut down for a day. I know it's kind of hard to imagine now, but every business was just shut down. Everybody was stuck at home. And so because of that, everybody started pulling on their insurance policies. And the Ohio Life Insurance and Trust Company didn't have enough money to cover all of these businesses. It was overextended, and it wasn't really there wasn't really a government entity in place to back up that insurance. And so the Ohio Life Insurance and Trust Company went bankrupt. And that kicked off the global depression of 1857. So what's interesting here is you can see, even a localized effect can have a vast global impact. And so that's an interesting takeaway for safety and reliability in complex systems. And it kind of gets into a little bit of chaos theory. I'm sure everybody's familiar with that old expression. If a butterfly flaps its wings in China, and that causes somebody to sneeze, that can cause a pandemic and an economic collapse halfway around the world. I think that's how that goes. Anyway, so yeah, the recession was caused by the success of this store. There's me in the photo, by the way. A few years later, I was out in Hayward, which is in the Bay Area, for those of you not familiar with California. And at the time, Hayward was, bustling, up and coming city. In fact, the whole Bay Area in California, it was, it had the nickname Garden of Eden. It had some of the most productive, most fertile soil in the world at the time. And so a lot of farming going on. Californians were prescient. Eventually, they learned to pave that over to seal the nutrients in the ground. But at the time, a lot of farming going on. And a friend of mine, this wasn't me, but a friend of mine worked for a fruit company. This fruit company sold apricots. And it was just a massive operation. They would essentially bring these apricot trees in crates, in like containers. And then they had this whole, again, massive operation to clear land and figure out the best place to place these containers for sunlight and water and all of that. And they had infrastructure to bring water in to water the trees. And one day, an engineer was hired to figure out a better way to more compactly place the containers. And he did, and he wrote that algorithm and put it into production. Unfortunately, the way that algorithm worked, it required the people digging the holes to come to a centralized table and scan a whole table every time they needed to move any of the containers anywhere, which basically caused too much traffic at this one base of data where they had this table. Everybody had to read the same table to make any of these moves. And that caused other things to queue up and stop and slow to a crawl. And for example, even backing out this algorithm required people coming to the table to undo that, and they couldn't get to the table because it's crowded with too many people. So the whole operation ground to a halt, and unfortunately, they had already built the infrastructure to pump water into this land. The land got saturated with water. It got too heavy, and the trees weren't there to soak it up and distribute it. So that caused the earthquake of 1868. What's interesting about this example, about this failure, this lack of safety here, is whereas previously we were seeing like, okay, there's these unanticipated consequences. Now we start to see like even in a system that's planned and fully engineered, we can have these unanticipated consequences that reverberate and impact at a system level, at a holistic level, and cause undesirable systemic effects. So in line with the experiences at the time, the one person who made that algorithm, they basically ran him out of town. I think he fled to Japan or something to be someplace where they didn't experience earthquakes. We didn't know a lot about geography back then, and they considered the problem solved. Right, they got rid of the person who had written the bad algorithm, and they figured that made the system more reliable going forward. Narrator's voice, that did not make the system more reliable. It's hard to see, but there's me in the photo. So in the 1890s, I was managing a couple teams in a helium mine situation. And I've got these things in the back of my mind of our intuition about more risk, like feels like it's less safe, and how do we think about the chaos theory where there's unanticipated consequences to decisions that we make. How do we actually make systems safer? Well, we had an experience where we ran short at a couple of these mines, and this helium mine, it was, we were cash strapped. Helium mining turned out not to be a great thing to try to mine for. And we had some engineers at submines who would basically find places where the cave collapsed, and they would spend all of their time getting really good at reinforcing those and reinforcing their defenses. And at some other mines where we had fewer resources, we basically had people who got really good at figuring out how to educate the engineers to as to whether the walls that they were digging into, the material that they were digging into, was soft or prone to failure. And we found that in the latter case actually had a better safety record. So even though they were working in mines that weren't being reinforced as often or as well, the engineers we found were actually implicitly making decisions that led to better outcomes. Here's me in that photo. And so this plays into a model later formalized by Jens Rasmussen that is kind of a foundation for a proactive approach to making systems more reliable. So in this model, there's these three pillars: economics, workload, and safety. And the model says that engineers basically implicitly change their behavior to optimize for these three things. You don't have to tell them to do this. And I'll give a software example. You probably don't have a rule at your company or wherever you work, or at a company that you even know about. There probably is not a rule that you're not allowed to spin up a million EC2 instances on AWS, for example. Why don't we have those rules? Obviously, that's a bad thing to do, and that's kind of the point. Engineers implicitly know that things cost money, and that if you run out of money, you're out of business, game over. So you don't stray too far from this economics pillar. You can kind of imagine that you're in the middle here, and that you're attached to each of these three pillars by a rubber band. And if you stretch too far, the rubber band will snap and it's game over. So everybody implicitly knows there's an economic pull, and that there's a safety margin there. The same is true of workload. Everybody knows that their servers can handle a certain amount of workload, and people can handle a certain amount of workload. And if you try to do too much, it's that rubber band's going to snap. It's just going to fail, and it's going to be game over. And the same is true with safety. The difference with safety and the other two is that most engineers don't have an intuition of how far they're stretching that rubber band from safety. They don't know what their safety margin is. And I'm comfortable saying that because we still have incidents. And we have incidents mostly because they're surprises. Be it an availability incident or a security incident, usually they're surprised because the engineers have no idea. If you knew that you were about to have an outage, for example, as an engineer, you would stop what you were doing and change something about the architecture so that the outage didn't happen. The same is true with the security incident. So if you're able to build up an intuition for engineers for what the safety margin is, they will implicitly change their behavior and make a more reliable system. And this is one of the foundational theories behind chaos engineering, which is something that we defined at Netflix when I was there, managed the chaos engineering team there. We have a manifesto of sorts at principlesofchaos.org defining chaos engineering as a proactive discipline to improve the reliability of systems. My favorite definition is this one. Chaos engineering is the facilitation of experiments to uncover systemic weaknesses. So we basically create experiments to identify the safety margin and feed that information back to software engineers, which implicitly changes their behavior to be more reliable. So one other point I want to mention with switching over to software with historical significance here's generally how we see software, or how the world sees software, well, how software sees itself. The chief merit of software engineering is its technical efficiency with a premium placed on precision, speed, expert control, continuity, discretion, optimal returns on input. I actually accidentally did this. So that's actually a description of bureaucracy. But from a sociological perspective, that's true. Software engineering is the bureaucratic profession. And I recognize this probably won't make it onto too many t-shirts, but it's true. No other industry in general does a better job of separating who decides what gets done from who decides how it's going to be done from the people doing the actual work. And the problem with that is that this is a model based on scientific management and Taylorism going back to the 19 teens. It's the wrong model for knowledge work. And if we think of ourselves as knowledge workers, and I tend to think software engineering should be knowledge work, then we essentially have the wrong model, right? So this would be better for a t-shirt, software engineering, doing it wrong since 1913. And most of the industry thinks that that's a good thing. If you think of, a typical team structure of a larger company, you've got people managers, product managers, project managers, tech leads, architects. All of those roles are designed to take responsibility for engineering decisions away from the engineers. And in knowledge work, that's the wrong model. So we end up with a bunch of myths about reliability, things that seem intuitive, but the data tells us is wrong. So for example, remove the people who cause accidents and you'll make your system more reliable. This is called the bad apples model of management. Unfortunately, this was tried in some hospitals in the United States a while back. We'll just get rid of the doctors who have the worst rates. But it turns out some people are attracted to the hardest problems and have the most experience dealing with the hardest problems. And so if you get rid of them, you could end up with worse outcomes because you're getting rid of the people who have the most experience dealing with the stuff nobody else wants to deal with. So that doesn't work. Second myth, you can make your system more reliable if you document best practices and run books. So I'm not saying you shouldn't document things. However, if you invest in this as a practice, you're not going to move the needle on making your system more reliable. And that's because making your system more reliable requires improvisation and adaptability to unique circumstances. And documenting best practices and run books just doesn't give you that. Myth 3, you can make your system more reliable if you defend against prior root causes. This is like defense in depth. This is like going in and making the known holes sturdier. Again, I'm not saying you shouldn't do that. I'm not saying you shouldn't patch things that are broken. However, that's not going to move the needle on reliability. That's not going to make your system more reliable because, well, for one thing, let's pick apart this prior root causes. In a complex system, and most of us in software are now dealing with complex systems. In a complex system, there is no root cause. And I'm really looking forward to the Q&A part. So I'll go a little bit further and I'll say, if you're currently doing root cause analysis, at best, you are wasting your time. Hopefully that kicks off some interesting questions. An example of the apricot farm, it was very clear to say, okay, that one person changed the algorithm. That was the root cause of the outage. But there's another narrative there. Removing that one person, saying that the algorithm was the root cause, fixing that doesn't make the system safer at all. An alternative narrative could be, why didn't the people who designed the table where that algorithm was implemented, why didn't they design that better? Maybe the root cause was, the people who designed that base of data or that table. Or maybe it was whoever was managing those groups who didn't have them communicate so that they didn't figure out how those things could have impacted each other. Or the director above them who didn't understand or place enough emphasis on safety to figure out the implications of that thing failing, or the VP above them who, understood that the infrastructure was built to bring the water in, or at the sea level, maybe it was the CTO. It was their fault for not prioritizing all of that, or investing in staging environments so that they could have tried some of these things out before they put the algorithm directly into production. So maybe it's the CTO's fault, or CEO's fault, right? Root cause is designed to find fault, and in particular, it's designed to find fault as low in the hierarchy as possible. So basically, root cause analysis is a method by the hierarchy to reinforce the hierarchy at the expense of the workers. So again, which of those is going to have a bigger impact on reliability? Changing the CTO's mind, or in their behavior, or getting rid of the person who changed the algorithm? Obviously, changing the system as a whole is going to have a bigger impact. Enforcing procedures will not make your system more reliable. Avoiding risk, the example I gave with the ships, doesn't work. Simplifying a complex system actually takes the business value out, because your business value is defined by complexity. Adding redundancy also does not make your system more reliable. We have as many cases of redundancy contributing to system failures as we have of it preventing system failures. So the theme here is don't fight complexity. You can't, but you can learn to navigate it better. So there's this evolution of CI to CD to CV. CI helped us make code faster and limit the rate of bugs being produced by getting the code together merged faster. CD helped us put that code into production faster by automating that process so that we can change our minds when the code is in production, roll forward quicker, things like that. And now CV says, okay, now that we can make code faster, get into production faster, how do we make sure that we still get the properties out of the system that we want, given all of that complexity that's quickly changing underneath? Just reading across the top, you'll start to see tooling coming out, already in 2019, but you'll see enterprises picking continuous verification up because it's a proactive experimentation tooling discipline that verifies system behaviors, whereas most of the stuff we currently have in the industry is reactive testing methodologies that validates known properties of systems, which is still good. It's just not helpful in navigating complex systems. So tools don't create reliability, humans do, but tools can help. If you want a free copy of this book, Chaos Engineering, that I co-wrote with Nora Jones, an O'Reilly book, you can go to this link here, and hopefully we have some time for questions.
Thank you, Casey. Very interesting presentation, and also some eye-openers for me. Very, your myths really hit are controversial, I can say. Like I have one question. One of the myths, it's the second one, I think, says like if you focus your effort on implementing best practices and runbooks, you're not helping making the system more reliable. But in my experience, if you have these runbooks and best practices, it also makes it easier for junior engineers to get onto the team. So isn't it really like not really a black and white situation, that you still need to have some of them, but it should not be the main goal of the team?
Sure. So like I said, I'm not saying don't document things. And it's a great way to communicate to other people how to come on the team. Sure, that's part of their education. But as an effort to improve the reliability of your system, if you see somebody say, you know what, we keep having outages, we need to really double down on run books and our documentation, that's not going to move the needle. There's if you have that kind of time and energy to invest in resources to improve availability, to improve the reliability of the system, to improve security, don't spend that energy on runbooks and documentation. Instead, spend it on collaborative exercises to figure out what the safety margin of the system actually is. There are much better ways to educate people, and the skill sets required to be to improvise during an incident are skill sets that can't be translated, that can't be transferred to another human through documentation.
Mm-hmm.
They have to be experienced. So whether in a simulation or in conversation or some other interaction with humans, you have to transfer the knowledge that way.
Okay. Unfortunately, we've run out of time, and our next speaker is already lined up. I suggest you check the Slack to see if there are any other questions. And thank you for your time and your presentation.
Thanks, everybody.